Hi everyone, and welcome to Eric's Electronics Workbench and part 2 of the Hewlett-Packard 8561E spectrum analyzer repair. Now if you haven't seen the part 1 video, I'll post a link to that video in the description below. You may want to check out that first video and you'll see the troubleshooting that led up to the point that we're at now. So the A10 module, that switch and Yig tune filter, has arrived. So you can see that right here. So with this module I'll be able to continue on with the repair. So the A10 module is no longer made, so the only option is to find a used module. Now this module is quite expensive, even the untested ones on the market, but buying an untested pull wasn't acceptable for this repair. I wanted a module that was guaranteed to function correctly. So I reached out to All Test Instruments. Now I've done business with them for over a number of years, buying used instruments and also repair parts, and I found that their service and products are exceptional. So I explained this repair situation, and they were able to supply the A10 module tested with a 90-day warranty. So definitely check out the Alltest website at www.alltest.net, or just give them a call. Alltest carries all the big names you trust in new and used test equipment, and they have an absolutely huge selection of test equipment in every category. You can be assured that each item leaves Alltest facility working to original specs backed by a 90-day warranty. Now, making accurate and reliable measurements means instrument calibration, and Alltest offers calibration service in their NIST traceable lab, where they can come to your facility for on-site calibration. Do you need something repaired but you're unable to do it yourself? Alltest has you covered there too. Talk with them and see how they can get your test equipment back up and running. And if you need to rent a piece of test equipment, Alltest offers that option as well. And finally, for facilities needing environmental test chambers, Alltest has extensive knowledge on all things related to environmental chambers: custom walk-in, repair service, rentals, refurbished, and more. So no matter what your test equipment needs are, get in touch with Alltest and see for yourself the quality equipment and the top-level services that they do offer. So this is the A10 module, but before I start any disassembly, I'll take a few photos of this area with my cell phone just for reference. It's handy to have those photos when it comes time for reassembly to make sure that there's no errors in the wiring, the routing, the coax, and so forth. So I'll get started with the disassembly and removing the A10 module. Okay, I've removed the coax from the low band out and the RF input on the A10 module, and the filter assembly that passed over the top of the module has been removed, so it's out of the way. And these two coax right here are just loosened on one end so they can be positioned to the side. And this coax is basically two SMA connectors back to back. Now I've loosened the nut on this SMA connector just a little bit, but you don't want to run this nut all the way back until the mounting screws are removed from the A10 module. So those screws are accessed from the other side of the instrument. They come up through the center deck in the spectrum analyzer. So I'll get to that next. But once those screws are removed, you just hold this module and then continue removing this nut and then just remove the module completely from the spectrum analyzer. Now the wires right here that plug onto these very delicate pins on the top, they just pull straight off, but you want to be careful not to bend these pins because there's a glass seal around the pin, so if you bend the pin you could end up cracking that glass seal, and of course that would ruin the module, so be very cautious of that. So let me get you zoomed out here and you can kind of see the rest of the disassembly here, how it looks. So pardon the camera movement here, just get this positioned up like so. Get you focused up here. Touch that up a little bit. So you can see how the circuit board folds out. There's actually two circuit boards here. You can see this circuit board is clipped onto the circuit board on the other side. And this portion right here covers this RF circuitry down here, so that's why this had to be folded out of the way. Now, normally when this instrument is turned this direction, this circuit board can just lay out flat on the workbench. But the way that the instrument is positioned with the top side down right now, this needs to be propped up. So I have a screwdriver right here. It's just holding up the circuit boards at this angle, because if the instrument is positioned this way and you try and let these circuit boards fold all the way down, it puts a lot of strain on the ribbon cables along here. There's some coax cables back there. It's really not meant to bend that far down. So keep that in mind when you're working on one of these instruments. But again, if the instrument is turned on its side this way, then this can just lay out on the workbench. And that's really how they intended it to be. So as always, if you're working on something like this, you're doing so at your own risk. Now, I know in this case there are no high voltages here, very low power, these wires, coax cables and so forth. There's really no danger here. But on the CRT and the power supply, which we'll see on the other side of the instrument, there are very high voltages. So again, if you're following along, you're doing so at your own risk. Be aware of where the high voltages are, use safety precautions as needed, and just take care and be safe. Alright, so I'll continue on the other side of the instrument and I'll show you when I have some updates. Okay, here we are looking at the top side of the spectrum analyzer. So of course it's sitting on its side right now, but you can see these two circuit boards are folded out, the other board underneath right there. And there are more circuit boards here that will fold out. So behind these circuit boards will give access to the A10 module screws, and also the power supply module is behind the circuit boards. Now the screws that hold these boards in place are not the same length. On the bottom side circuit boards, all the screws are the same length, but again, there are different lengths on the top here. Let me grab these samples over here, and you can see these are the 3 different lengths right here that are used. So there's a handy chart that's printed right here, and you can see the legend that's printed has a full-scale, full-size drawing, and there's a 4, 3, a 1, and a 2. So those identification numbers are printed on the circuit board next to the hole for each screw. So if there's a 4 next to the hole, then of course you know to use the longest length of screw and so on. All right, so let me get you zoomed in a little closer, and you can just take a quick look at these bottom circuit boards here. Pardon the camera movement. Lift this board up here, and you can see quite a bit going on those boards, that's for sure. Definitely packed a lot of electronics into the spectrum analyzer. So put that back down and positioned up here. So I just need to tip these circuit boards outward here, so that just pops out. Just have to watch these ribbon cables, you don't want it to catch there. So you can see there's 2 different circuit boards here that are connected together. There's a plastic clip right here, so if you need to separate these, you just pull that plastic clip out a little bit and these 2 boards will separate apart. Alright, so get that over there. So that just lays down like so. You can actually operate the spectrum analyzer with everything open like this for servicing. Alright, so that gives us access to the inside there, and right here are the screws for the A10 module, so that's what I need to remove, and the power supply is behind this shield right here. There's some more servicing data that's printed on there. So I'll begin removing the A10 module, and then I'll reinstall the replacement module, and we'll continue on. Okay, so the defective A10 module has been removed, and the replacement module is mounted in position, but I don't have the coax or the wiring attached yet, and I'll do that in just a moment. Now I noticed on this module there's a date printed on the bottom, and it says June 14th of 96, so probably the original module in this instrument. And the replacement module had a date printed on the bottom. It was a little bit faint and hard to read, but I think it said 1998. Looks like a little bit newer, and the serial number is a little bit newer than this module as well. Now the final step that I'll need to do is to calibrate the replacement module, and I'll take you through that process. And one of the steps in the calibration procedures is to move this jumper right here. So this is an EEPROM protection. There's a write protect and a write enable. So of course it's in the protection position right now. This little black colored portion is unplugged and just moved over to the other position. So when I get to that point in the calibration process, I'll mention it, but I won't show this again. I just figured I'd show it now since the circuit board was open. Now, when this circuit board is folded back up into position, you can still reach this edge, so you don't have to unfold it to move that jumper. Alright, the replacement A10 module is installed and everything is reconnected to it. Now this coax right here connects to the sampler's RF input, so I'll make that connection when the circuit boards are closed and back in position. So I'll do that next. And then let's check out the spectrum analyzer and make sure that it's functioning correctly. So we want to make sure that the low RF band is working the way that it's supposed to, because of course that's where the problem was initially. And we'll also look at the high RF band, but I suspect the high RF band may have some errors because it hasn't been calibrated yet. But if everything looks like it's working close to the way that it's supposed to, then we'll move on to the calibration procedures. So the calibration for the A10 module affects the Yigtune filter, and the Yigtune filter is only used on the high RF band. Alright, let's check out the 8561E spectrum analyzer and see if it's functioning correctly, and if it is, then we'll move on to the calibration on that A10 module. So I'll go ahead and power it up. So that squawk sound is just the internal speaker. It makes that noise when it first starts up. So it's going to run a self-test and some internal alignments. So I'll give it a moment here. You can see on the screen coming up right here is RF adjust and the IF adjust. So it says RF adjustment is done, and a few more things on the IF adjustment there. Okay, perfect. So no error codes and all the internal adjustments are done. So let's take a look here at the calibration output signal. So as you recall in the part 1 video, the signal that came out on here, which is a 300 megahertz minus 10 dBm signal, was displayed much too low in amplitude. and any signal that was applied to the spectrum analyzer was out of spec and too low on the amplitude value, although the higher the frequency it improved, but it never was perfect even all the way up to 6 gigahertz. So let's go ahead and see if this is now displaying correctly on this reference signal, or at least very close, and then if it is, we'll connect it over to my Rohde & Schwarz SME06 RF signal generator, and we'll take some more accurate measurements. So, like that, and let's get this connected over here. Yep. So you can see some signals over here and some harmonics. So let's put 300 megahertz in the center. So frequency, center frequency will be 300 megahertz. And let's make the span, let's say 100 kilohertz. Okay, perfect. So there's our 300 megahertz signal. Now the reference level at the top, so the top graticule, is 0 dBm. And we can see it's down 1 graticule, so that's perfect because that would be minus 10 dBm. That looks very good, so excellent. So we put the marker on it here, peak search. All right, so very close. It says the marker is minus 8.93 or 8.83. I think it's 8.83 dBm. And of course the instrument just turned on, so it's not even warmed up yet and settled in, but that's again very, very close. So before, it was way down. I think it was like minus 40 dBm, something like that. So no problems there. That's looking very, very close and really where it should be. And this calibration output signal is quite accurate, but the most accurate signal will be out of my Rohde & Schwarz SME06, and we'll get to that in just a moment. So yeah, excellent. So now, yeah, it's settled in. It's minus 9 dBm, so that's only 1 dBm off. So I would definitely say that the problem is solved, at least on the low band. We'll take a look at the high band and see what's going on there. And again, the calibration will affect that high band. So it looks like the low band is working, and that really does confirm that the other module is faulty. So perfect, excellent, good start on here. So let me do this. The next thing is actually we need to set the reference level adjust before we do any other calibrations. So let me get this connected over to my Rohde & Schwarz signal generator, and actually before that, the Rohde & Schwarz, we need to make sure that the output signal is exactly, we'll go with a minus 10 dBm signal and then make the calibration adjustment on the reference line. So for that, I need to connect it over to my power meter, and we'll take a look at that next. So let me do that. So to do the testing and calibration on the spectrum analyzer, I need to have an RF signal that has a very stable amplitude and frequency. So we have to allow for the loss that's in the cable between the signal generator and the spectrum analyzer's input, because it is a measurable loss. So right now you can see on the display it says minus 10.5 dBm, basically 10.511, so about 10.5 dBm. Well, the signal generator is set to minus 10 dBm, so there's about a half dB loss in the cable, and that's reasonable, it makes sense. So the cable I'm using is actually an RG223, so it's a very low loss type cable, but there is a measurable loss nonetheless. So what I have to do is increase the output of the signal generator just slightly to offset the loss in that cable. Then we know that this point right here, which is going into this power sensor, this will be connected to the spectrum analyzer, and we know that we're getting exactly a minus 10 dBm input to the spectrum analyzer, so that when the displayed value on the screen says minus 10 dBm or whatever level we're at, we know that it's accurate. Because again, we don't want to be a half dB off on our measurements, and you can see that that is occurring right now. This display up here, you can see it's minus 10.5 dBm, and then that's the actual wattage, so 88.9 microwatts. Now, let me just move this over here. Pardon the camera movement. I'm just going to swing this over to the signal generator just this one time so you can see the setup over here. Pardon all the movement. It's way around over here. So that's the SME06, and you can see that right up here, right there is the output level, so you can see it's set to minus 10 dBm. And if that power sensor were connected to the output of the signal generator, move this over just a little bit more, so you can see right over here is the output cable. If that power sensor were connected right there, it would be reading minus 10 dBm. This is a very accurate output on the signal generator. But again, we have some loss in that coax. So let me move this back around over here. Pardon the camera movement. Just swing this back around. So it's really just a simple matter of increasing that output so that we get exactly minus 10 dBm on the power sensor. in the display over here on the power meter. All right, so I'm going to increase the signal generator's output just a little bit. We'll get this right at minus 10 dBm, and then I'll connect this over to the spectrum analyzer. And let's set the reference level. That's the first thing I need to do. So I'll make some adjustments here and we'll continue on. All right, so I have that accurate minus 10 dBm signal connected to the spectrum analyzer's input, and we can see on the display we are showing minus 10 dBm, or very close to that value. So I need to adjust the reference line, and we'll get to that in just a moment. So on the spectrum analyzer's display, the very top graticule is currently set for 0 dBm, and you can see right here it says RL and then 0 dBm. So that means that this very top line is the 0 dBm reference. So right here it says 10 dB and then a slash, so that means that each graticule is 10 dB of difference, and so the signal, the lower we go this way, the smaller the signal level, and this of course is noise level down at the bottom. Well, we are down 1 graticule, so that's minus 10 dBm. So if you go another graticule to minus 20 dBm and so forth. So if we count here on this display just the way we're looking right here, that would be 0 and then 10, 20, 30, 40, 50, 60, 70, 80. So you can actually see down to minus 80 dBm before you're just above that noise level. So that's a huge range. Now, if you're not familiar with what we're talking about when we say dBm, you know, and what that scale means and what are those values, and if you're new to electronics, maybe new to RF measurements, let me just give a quick explanation about what the dBm scale is all about. So 0 dBm, this reference line at the top up here, 0 dBm is referenced into a 50 ohm impedance because that's the impedance that's very common in RF circuits like we're using here, and coax cable and so forth. That reference impedance could be different in some cases. It could be 75 ohms, it could be 300 ohms, 600 ohms, so be aware that that can vary, but again, 50 ohms is very, very common, particularly for RF work like this. And what it means is that into 50 ohms, you're dissipating 1 milliwatt, okay? So 0 dBm is 1 milliwatt. And 1 milliwatt in 50 ohms, that works out to 223.61 millivolts RMS. Now, let's say you go up in value to plus 10 dBm. Of course, on here, that would be off the scale as it's shown right now, but it could be adjusted to show a plus 10 dBm signal. Well, plus 10 dBm is 10 milliwatts, and that's 707.11 millivolts RMS. Well, that's 10 times the power that we were at 1 milliwatt. Okay, well, that's a big increase, 10 times the power level. Now, 10 milliwatts may not sound like a lot of power, but it's 10 times as much. Now, let's increase that again. Let's say you go to plus 20 dBm. That's now 100 milliwatts, or 2.24 volts RMS. So 100 milliwatts into 50 ohms. And let's say you go now to plus 30 dBm, that's again 10 times as much, that's 1 watt. So 100 milliwatts times 10, you're at 1 watt. That's again a big increase in power. And 1 watt and 50 ohms, you're at 7.07 volts RMS. And you can continue on, plus 40, plus 50, and so on. And every time you're increasing by 10 times as much. So you have a logarithmic scale. Now, if this was a linear scale on here, there's no way that you could have that same range displayed. Think of a typical oscilloscope and the voltage. Maybe you're at 2 volts per division, 2, 4, 6, 8, 10. You're very limited. But on here, that range, when you're talking about 223.61 millivolts RMS at 0 dBm, let's go all the way down to that minus 70 dBm. So you're way down here just above the noise. Suddenly you're at 70.71 microvolts. So that's a huge difference in power level. So if you're at minus 10 dBm, which is where we're sitting at right now, that's 100 microwatts, or 70.71 millivolts RMS. And then let's say you decrease down again, that would be minus 20 dBm, or 10 microwatts, 22.36 millivolts RMS. So again, it's a factor of 10 that you're decreasing by. So I think with knowing that, you can appreciate the range that can be displayed on here. When you see this amplitude vary up and down, particularly by a full graticule, it's 10 times the power difference. So again, a big, big change. And going all the way down minus 70 dBm, again, that's 100 picowatts, very small power level, 70.71 microvolts RMS. Now, why is this so useful and why is it displayed this way? Think of the ranges that you deal with RF power levels. A receiving antenna, you're down in the microvolts. They're very, very small voltages that are induced in the antenna. Think about just a typical radio or something like that. So you are dealing with microvolt type signals, and in fact, if you connect an antenna to the spectrum analyzer, you can pick up, say, broadcast type FM stations and so forth, and this will demodulate, and you can actually hear the audio on FM stations and so forth. So this certainly has the ability to pick up those very small microvolt signal levels. But at the same time, think about a radio transmitter. you could be up in the 1 watt, 10 watt, 100 watts, kilowatts of power, and again, such a huge range. The logarithmic scale and the decibels, dBm, it really is the best way to display such a wide range in power levels. So I hope that explanation helps those of you who are new to RF measurements, and maybe you're new to electronics and this idea of the dBm scale and what did that mean. Hopefully this clears that up and makes it a little bit easier to follow. All right, so let's take a look at the reference level. So what we need to do is actually put this peak right here at the top graticule. So I need to set that top graticule at minus 10 dBm to start with. So I'll go ahead and do that. If we hit amplitude, actually we're on that right now, reference level, so we want to go minus 10, just like so. Okay, so you can see that puts that peak right at the top, but actually the peak, it looks like it's just above. It may be a little bit hard to see on the camera, and what I'm going to do is zoom in a little bit closer here so you can actually see that display a little bit better and kind of be able to follow what I'm doing here. So this peak right here, we actually want that peak just to touch that top reference line, and to my eye it looks like it's just a little bit over, so that needs to touch. And again, we know we have a very accurate minus 10 dBm signal going into the spectrum analyzer. So over on the calibration menu, just hit the cal button, and right here it looks like reference level adjust right there. So the reference level cal is at 220 right now, and if I just take the knob here and turn this, should begin to affect that. I think we want to maybe go the other way. Where are we at here? Yep, there, it's coming down just a little bit. Just want that to touch that top line. It has decreased just a little bit, so now I'm at 147. Ideally, this reference level of value should be close to 0. That's what the service manual calls out. So it's nice to see that we can actually bring it back down from where it was. The old A10 module would have affected this because the signal, of course, passes through that module, and for whatever reason it may have had some more attenuation because the reference level was basically being increased higher than it needed to be. So I'm going to just decrease that a little bit more here, but okay, it looks like right there, I think we're really close. The peak of that signal is just touching the top graticule. Perhaps I should go up just a little bit more. It's 130 right there. This 130 value, that's just an arbitrary number. It's not in voltages or dB or any such thing. This is just a reference number. So this peak right here, I think that really looks good. It's just touching that reference line right there. So I think that's right where it should be. So I think we can call that good right now. That should be acceptable. So now I just need, it says store reference level, so I want to do that. So that's now in the memory, and it will hold that for infinity until it's changed again, so no problems there. That's perfect where it needs to be. Okay, so let's take a look at, let's say, a higher frequency. Let's go up to 1 gigahertz and see if it's displaying that value correctly. Actually, we're at 300 megahertz right now. Let's go down in value first and just double check a low frequency, and then we'll work our way up instead of jumping all over the place here. So we're at 300 megahertz. Let me go down, let's say 10 megahertz and check, because before 10 megahertz was way off on its displayed value. So let me just go over to the signal generator and I'll go to 10 megahertz, frequency 10 megahertz right here. Okay, there it is. So let's take a look here. Frequency, center frequency 10 megahertz. Perfect. That looks very good. So the reference level or amplitude coming in is still minus 10 dBm, so that's perfect. It's just touching right at the top. So no problems at all. Again, minus 10 megahertz before with that old module was way down low. It was way out of spec. So this looks excellent. So now let's jump all the way up to say 1 gigahertz. So say frequency 1 gigahertz. Here, frequency 1 gigahertz. Perfect, no problems there. So again, coming right up to that top Radicule. So let's try the high band. So everything we've been doing right now is in the low RF band, and it switches over, I think, just prior to 3 gigahertz. So let me jump up. Let's try right at 3 gigahertz here. Frequency 3 gigahertz, like so. Frequency 3 gigahertz. And yeah, okay, now that's way off. So now this is where the calibration is probably going to change that. So this is now in the high RF band. You can see it's displaying a very, very low signal. So let's hope that the calibration corrects this. We're going to find that out. And just for the sake of completeness, let's try, say, frequency 6 gigahertz. Let's just jump up all the way to the top. Say frequency 6 gigahertz. Yeah, it's way down there. It's very, very low. So hopefully the calibration will bring those values up into the range that they're supposed to be, because this should be clear up at minus 10 dBm. All right, so let's continue on with the calibration procedure. I'm going to get some paperwork in order here. So I'm basically following the instructions right out of the service manual for the spectrum analyzer. Just printed out the page here. So let me get that in place and go over here to 3 gigahertz. Set that back over where it needs to be, because we're going to start at 3 gigahertz for the first part of the calibration procedure. So what I will do, say frequency 3 gigahertz, like so. All right, so the procedure says to set the line switch off, disconnect the power cord, remove the spectrum analyzer's cover, and connect the line cord. Okay, well obviously we've done all of that because the thing's open right now. And connect the equipment as shown. So they're basically showing you to connect the signal generator in and do the things that we've done so far. Get the signal up to the spectrum analyzer. And then they want you to move the right protect, enable, and that jumper on the A2 controller circuit board to the right enable position. So I'm going to reach around to the side and I'll get that jumper moved over into the right enable position so that we can make the changes to the calibration constants. Okay, so the right protection jumper is moved over to the right enable position, and I did a preset on the instrument, so that just gets it to a known state. And the input here is 3 gigahertz at exactly minus 10 dBm. I adjusted the signal generator like I showed before, so it allows for the loss that's in the cable. So the next thing that we need to do is set the center frequency to 3 gigahertz. So go frequency and center frequency, it's there, 3 gigahertz, like so. And they want to do a span of 0 hertz, so 0 span. So span 0 hertz. Okay? And then it says what we need to do is press the cal button, so do that. And IF adjust offset. So I'm going to do that right here. Let's see, IF adjust there, off. More 1 of 2. Hit the service cal data, so that's right here. That service cal data comes up when that right protection jumper is moved over, otherwise that's not available in the menu. And then pre-select adjust. So pre-select adjust right here. And this is preset all DACs. So right here, preset all DACs. Okay. Alright, so then it just reminds us to have the signal generator at 3 gigahertz minus 10 dBm. So everything is set on that. It says press pre-select offset. So it's this right here. Use the front panel knob to peak the displayed trace and record the offset DAC value below. Alright, so we'll grab a pen here and okay. So right here it says offset for band number 1, which is the high band, and it's currently set for 128, so that's again just an arbitrary value. But what we want to do is peak this trace, so I'm not sure exactly which way we need to go. Decreasing down. Aha! Look at that. That makes a big difference there. Oh, look at that. It's right up there at that minus 10 dBm line too. Very cool. So it says to peak it. So I think, yeah, right there. Find that peak. No, missed it there. So I think 70. That looks like the peak right there. So that goes down 70, 69. Yeah, I'm going to say 70. So that number right there, 70. So it says, just to record that, so I'm going to make a note here, we're at 70. Okay. So the next step it says to do is to set the center frequency in the signal generator to 6 gigahertz. So center frequency, 6 gigahertz. And let me reach over here and adjust this. So we've got frequency, 6 gigahertz. And the level adjustment here, calibrated in. Okay, there we go, 6 gigahertz, and then the offset, so I'm compensating for the loss in the cable. Okay, so now it says to press cal, more 1 of 2, service cal data, pre-select adjust, pre-select offset. It says key in the offset value noted in step 6 above, so it was 70, so it's actually, it says 70 right there, so just to make sure we just go 70, okay. Press pre-select slope. Use the front panel knob and peak the displayed trace and then record the value. So let's try that. So right now it's 128. Immediately starts coming up. And I think we hit the peak right there. Missed it there. It's 155. 157. I'm going to say 157. Yeah. Yeah, 157 looks like about at the peak right there, so make a note of that. 157. Alright, so it says now to set the center frequency and the signal generator to 3 gigahertz. So go back to frequency, 3 gigahertz. So let me reach back over here to the signal generator, go back over to frequency, 3 gigahertz. And I need to get the level calibrated in. Okay, there's the signal generator reset. In the spectrum analyzer, press cal. So we'll do that. 1 of 2. Service cal data. Pre-select adjust. Pre-select slope. Key in the slope value noted in step 9 above. So it was 157, so it's already there, but we'll just do 157. And pre-select, okay, so 9 above. I did that, enter that. It's going to be an enter. Okay, there it goes. Okay, perfect. So we've got that. Now it says to repeat steps 6 through 11 until both the slope and the offset are peaked. It says adjust the offset only at 3 gigahertz and the slope only at 6 gigahertz. So I'm going to repeat this several times to make sure that's peaked up, and then we'll continue on. I won't show that on the camera because it's the same steps I've just done. I'm just going to do them several more times. So I'll continue on. Alright, so I had to go through the calibration procedure 7 times, and on the 7th time no further adjustment would peak the displayed trace. So then the calibration is complete at that point. So the actual values for the offset ended up being 70, then 90, 100, 104, 107, 108, and then 109. So you can see the numbers got a little bit closer as the calibration procedure went along. And then the slope values ended up being 157, 171, 178, 181, 183, 184. So it's complete at this point. Again, no further adjustments will peak that trace, so we're looking very good at this point. So now the next step, it says, is to press the previous menu. So right here it says previous menu, so we'll do that. And then store data. So we have that right here, yep, store data. And yes. Okay, so data is stored. And then it says to place the right enable jumper back to the protection position. So I will reach around on the side of the instrument and do that. Okay, that is complete. And the final step here looks like on the spectrum analyzer, press recall. So where are we at here? Recall is going to be over here. More 1 of 2, so that's right here. Factory pre-select peak, so factory pre-select peak, so they want you to press that. And save. And save pre-select peak, so that looks like right here, save pre-select peak. Alright, so that looks like the calibration is complete at that point. Let's take a couple measurements and see how the spectrum analyzer looks. So let's do this here. Do a preset. So the signal generator is at 3 gigahertz, so we'll go frequency 3 gigahertz and span 100 kilohertz. Hey, look at that. Not too bad. That looks really good. So minus 10 dBm, that's second graticule down. So let's do peak search. And what do we see? So the marker is at minus 9.67 dBm. Really good. I don't see any issues with that. That's so close. Very, very close to that minus 10 dBm level. So calibration successful. It looks like it's working very well. So let's try 6 gigahertz. So jump over here to the signal generator, go to frequency 6 gigahertz, and correct the level so we compensate for the coax. So let's see, here we go, frequency 6 gigahertz. And let's do a peak search. Span is still at 100 kilohertz. And that's spot on, look at that. Minus 10 dBm. Perfect. So this spectrum analyzer is functioning very well. So calibration successful and repair successful. So if you enjoyed this video, please remember to give it a thumbs up, and if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. So as always, thank you for taking the time to watch, and until next time, take care. Goodbye for now.